Hi everyone, welcome back. So this week we're talking about adding induced subduction into the world generator simulation, and let's get started. So the agenda for today, we're going to have a quick recap of the theory of what we're trying to achieve and why. Then we're going to look at some demos to show where we've got to and how it's working so far. A quick status update and a brief discussion of what we are doing next, what we're hoping to achieve over the next week or so. So, to recap the theory, natural subduction happens when a plate gets old enough that it cools down, densifies and starts to sink into the mantle. Induced subduction is where two, usually ocean plates, although it could be one ocean and one continental, collide, and the denser crust gets forced underneath the less dense plate. Now, in our model previously, what would happen is the plate would just continue moving until the crust was cold enough to sink naturally, and this would extend massively out to the side. Not very realistic, also slows the simulation down a lot. So what actually happens is once the piece of oceanic crust is forced underneath the other plate, the extra pressure and temperature at this depth will start to cause a process called eclogization, where the basalts transform into a denser type of rock called eclogite. Once enough of this has occurred, the plate is denser even though it's still hot, and it's dense enough to start to sink even though it's hotter than it normally would be, which means it sinks earlier, tends to sink at a slightly shallower angle, and yeah, that's what happens. So this will stop that problem of plates growing too big. It should also smooth out that plate motion, because we'll have a lot of different rates of sinking, and they will be induced at different times, whereas we were getting problems with bands of subduction occurring and then stopping, and this should smooth all of that out. So let's quickly look at a few demos. So this is the first one. We have a plate here, we're in the plate view, and if we set it going, we have added a new, we've enhanced the crust type. So this darker blue now represents subducting points, so you can see what's subducting and what isn't, and this was very helpful. So we've got natural subduction occurring along here. This is just showing that the existing thing was still working. You can see a nice temperature gradient moving across, subduction occurring. And that's all we really need to look at on this one. We have another one here. So this plate, you can see the crust is all getting to the edge without reaching its natural subducting point, and as soon as it does, it starts to subduct. And we can see here the temperature is too high for it to naturally subduct. This is our induced subduction model working, and this is a really clear demonstration of it working. There isn't much of a shelf while eclogization is going on. It is there, you can see it at the right angles. I have double checked that. It doesn't tend to be very wide. I think the crust isn't actually moving at full speed, but I'm not tuning any of this until all of the dynamics are in place. There's no point, I just have to redo it again every time. So this is working as expected, and as you can see, we now have crust that actually follows the shape of the edge of the plate. Not exactly, there's various dynamics that avoid it being an exact one-to-one, but it's pretty close. And you wouldn't want it to be an exact one-to-one. It's not supposed to be. Those dynamics are things that we want. So now if we move on to this one, so now we can see an interesting case where we have a very narrow plate relative to motion. Now it looks like it's moving backwards, it's not, that's just an artifact of the frame rate. So what's interesting here is that the crust doesn't have much time at all to cool, and our model accounts for how cool the crust is before the eclogization process starts, and that means you end up with a very long, very shallow subduction leads to a very long subducting slab. This, I believe, is realistic. It's certainly as realistic as I want it to be for this simulation, as I need it to be. There's sort of an interesting feedback loop here where, because this is shallower, it means there's more crust subducting, which means it probably pulls the crust faster, which means it's even it has even less time to cool before the subduction starts, which again then means it subducts more shallowly. Like I say, feedback loop. This is slightly countered by the fact that the shallow subduction applies less force per point, but you have more points. Whether they fully balance or not, I'm not actually sure. I need to check the maths on that. Either way, we get a good result, and a plausible result, which is what we're looking for. And now we have one more to look at. So the interesting thing here is, before I even play this, you can see we have subduction here, which is happening before we get to the edge. So this is natural subduction, and if you look at it, this sort of mirrors the shape here. And what's happening is there is a natural limit to how big a plate can be based on how long the crust can last before it cools enough to subduct and how fast it's moving, and we are hitting that rate here. As you can see, that you get these bands of temperature that follow this. So it's interesting that we have shape information from the leading edge being transferred over to the trailing edge. What I expect will happen when we have moving boundaries is that we'll have a new plate start. This will become a spreading ridge, and we'll have a new plate start to grow into this gap here, and eventually that plate will start to cause forced subduction just through the ridge push. Will keep it moving, and eventually I would imagine that plate will completely override this plate, and we'll probably end up the same shape but moving in the opposite direction, ironically. And obviously we'll have other plates around here, and a lot of complex forces to see what will happen. But yeah, it's quite cool to see this transfer of information from the leading edge to the trailing edge. And yes, and then we have the induced subduction happening out here. So basically this is showing all of the subduction dynamics that we wanted, and all fully working now. So I'm really pleased with this. This is basically, subduction is now done. And in fact, if we have a quick look at the status slides, as you see, induced subduction here is now ticked off. And in fact, all that's left now for our oceanic crust simulation is moving boundaries. That's quite a complex thing. That's going to take me a while to do. That's the next big thing. Dehydration and hotspots, they should be fairly trivial. And then the global remapping, again, not worried about that. That's a computer science thing, not a geology thing. So yeah, we're in quite a good place here, I think. And sort of we have one big complicated thing left, and then some simpler things. So I was hoping to move on to this this week, but actually this induced subduction turned out to be more complicated than I was expecting. I was saying it was one piece of state to track. It actually turned out to be several pieces of state which interacted in non-trivial ways with some of the existing simulations, so I had to go back and rework some of that. But we got there, and it's working, and this is good. So what are we doing next week? So next week I'm hoping for a bit of a consolidation week. I don't know if anyone noticed on the videos, but the frame rate was much lower. We're still well within budget, or I think we're about half budget. I want it to be faster. The development experience was a lot nicer when it was faster, and also there are some very obvious wins that are very easy, so I'll get a profiler on it, check that they are the things that are slow, and go and make some improvements. And then some refactoring. Bits of data aren't really in the place I need them to be for the moving boundaries, so I need to get that sorted out. Those two things will probably consume the whole of this coming week. Possibly I'll get onto moving boundaries. If I do, that would be great, but no promises. So that's it for this week. As ever, thank you for watching, and any suggestions, any thoughts, very welcome. Thanks again, and I will see you all next week.